Okay, so yesterday in lecture we started talking about covalent bonds, and we said covalent bonds are when you share electrons between two neighboring atoms, and this usually occurs whenever there's a small difference of electronegativity, meaning they're willing to share it, they don't want to steal electrons. And we said that usually covalent bonds occur between nonmetals, so the right-hand side of the periodic table. We said the easiest thing to do is to first draw out those atoms with all of their valence electrons as Lewis symbols, and then try to connect up the unpaired electrons as bonding pairs. So for the example with chlorine, you can show those bonding pairs as a single line. We then briefly talked about what happens when you need to form double bonds. So in the example of oxygen here, we could actually form two bonding pairs and have an octet of electrons around each oxygen. What we need to do today, though, is introduce a new topic called polar covalent bonds. So let's get started with that. And we'll do this by a counterexample with the nonpolar bond. And a nonpolar covalent bond is described as a bond where electrons are shared evenly. Between two atoms. Typically, this only occurs if you have a very small difference in electronegativity. And typically, this difference in electronegativity, using that table I showed you yesterday, is going to be between about 0 to 0.5. I don't expect you to know those numbers off the top of your head. I would give you a table. In general, a good example for a nonpolar bond would be something like a carbon-hydrogen bond, where the difference in electronegativity is about 0.4. So really, they're sharing those electrons in that bond relatively evenly between those two atoms. One's not hogging it more than the other. This is different than a polar covalent bond, where you can imagine in a polar covalent bond, electrons are not shared equally. And typically, this occurs anytime you have a large difference in electronegativity. And typically, this range for electronegativity is going to be anywhere from about 0.5 to 2. Does anybody know what happens if you've got a difference in electronegativity greater than 2? Thinking back to yesterday's notes. What was the other type of bond? It's an ionic bond, right? So if you have a really, really, really large difference in electronegativity of greater than 2, there's actually a transfer of electrons, not a sharing of electrons, and it becomes ionic. So let's make a note of that. So if your difference is greater than 2, then the bond is ionic. Does that make sense? I always imagine it as a tug of war between two atoms, right? So if you've got two atoms of equal strength, it's kind of a tie. But if one atom is stronger than the other, the tug of war is out of balance and the bond becomes polar. So let's take a look really quick at an example. Let's do HCl. It's hydrochloric acid. It's what helps you digest food. And if we try to draw out the structure for this, we know that chlorine has 7 valence electrons and hydrogen has 1, so we can immediately pair up the unpaired electrons. And we can make our Lewis structure that looks a lot like this. Now the tricky question is, without looking at the table from yesterday or in your book, which atom do you think is more electronegative, hydrogen or chlorine?
Hydrogen is closest electron.
Yeah, if you remember, the trend is towards the top right-hand corner of the table, and chlorine's closer to that top right-hand corner. So chlorine's more electronegative. And in fact, if you use the table, the difference in electronegativity is 0.9. And we know that chlorine is more electronegative. Let me make this bigger. Does that make sense? There's a bunch of different ways you can draw this. So I wanted to show you some examples of how to draw bond polarity symbols. And I think I lost my picture here. Sorry, just one second. So let's determine how to draw bond polarity symbols. Oops. That just means difference. So in math, that triangle means delta, meaning a change. Good question. So let's take a look at HCl. So I'm just going to redraw the Lewis dot structure. One way of showing a polar bond is with this special type of arrow. It looks like that. And basically indicating that the chlorine is pulling electron density towards it. And then at the end of the tail, you put a plus sign, meaning electron density is being pulled away from the hydrogen, which means that this chlorine is electron rich. It's tugging on the electrons in that bond. And this hydrogen over here is electron poor. Another way of drawing this, instead of using the arrows, is slightly different, but you may occasionally see it, so I want to show it to you. And that's using a delta symbol. So for example, the chlorine over here is electron rich. It's not a full negative, but it's partial negative, so you use a lowercase delta with a negative sign. So that means it's electron rich. And the hydrogen on this side is electron poor, so you do delta positive. Same symbology, though. Both mean the same things.
It's not an arrow above the hydrogen, right? Is it just a line?
Above which one? The left one or the right one?
On the left one, there's an arrow, the red arrow. Is that
Yeah.
just a line above the H?
Yeah, so this arrow right here has an arrowhead on one side and kind of a plus end as its tail. Does that make sense?
Yes.
Okay.
What's the symbol above the other?
So on the right-hand side?
Yeah.
So it's a delta symbol. It's a Greek symbol. If you're uncomfortable drawing that, you can go with the other notation.
Okay.
I just like to show it both ways because I never know further on down the line in biology or in your other chemistry classes if they'll show it one way over the other. So I like to show both ways. Does that make sense? Okay, let's try another one. And I want us to practice using bond polarity symbols. So let's do NH3. And I want you to first draw the Lewis dot structure using the bond lines and lone pairs and things like that. And then I want you to have bond polarity arrows for any individual bond that has an imbalance of electrons. So I'll give you guys a minute to practice this. I know the periodic table is hard to see here, so if you have one in your bag or in your textbook, you might want to pull that out. If you think you got it, give me a thumbs up too. A few people. All right, let's try this as a class. I apologize for rushing. First thing I do is I kind of stagger my atoms around. We know we've got 1 nitrogen and 3 hydrogens like that, right? Easiest thing to do is put the heaviest atom in the middle, which is nitrogen in this case. All right, how many valence electrons for nitrogen? 5. So I go 1, 2, 3, 4, 5, like that. How many for hydrogen? 1. So I go 1, 2, 3. Again, we compare these up like that. And now we can redraw this using bond lines, showing those bonding pairs of electrons. And we can't forget the lone pair on nitrogen that's left over like that, right? So this would be our overall Lewis dot structure for ammonia, NH3. Now the question is, which atom is more electronegative, nitrogen or hydrogen? Nitrogen. It's in the top right-hand corner. So what you can do is say, all right, this nitrogen is going to steal electron density from that hydrogen, so you can show an arrow like that. It's also going to steal it from that hydrogen, so you can show an arrow like that. And then it's also stealing electron density from that hydrogen, so you can show it like that. Does that make sense? It's tugging electron density from all 3 sides. All right, let's do one more. We'll do a really easy one. We'll do H2O, water. And I'm going to get us started, and I'm actually going to put oxygen in the center, hydrogen right here, hydrogen right here. How many electrons around oxygen? 6. Okay, so I'll go 1, 2, 3, 4, 5, 6. Hydrogen has 1 and 1. And we'll go ahead and circle these and circle these. Sorry, I lost my dot in there. Okay. So now what you can do is draw it out like this. However, what I notice is some students will draw it like this, and other students will draw it like this. The truth is, for Lewis dot structures, both are correct for Lewis dot structures, but one is more correct than the other, and we'll talk about that next. So either one of these is an appropriate way of drawing a Lewis dot structure. All right, which one's more electronegative? Oxygen, absolutely. Fluorine, oxygen, and nitrogen are the most electronegative. So it's going to pull electron density away from this one. Same thing with this one. And I'm just going to make a note here that this version on the bottom is the better representation. Does that make sense? All right, how many of you have that green handout I gave you yesterday? If you don't have it, I've got a few spares up here from yesterday, so you can grab one. You can also share with the partner. But what we need to talk about next is why the lower version of water is actually the better representation. And I'm going to redraw our examples with water, just so we can get a rough idea of why there's a problem here. So these were the 2 different ways we had for drawing structure. We said both are correct according to the Lewis drawing system that we saw, but we actually know that this angle between the 2 hydrogens and water is closer to 108 degrees. We can experimentally measure that, which means that this one where we show them 180 degrees apart isn't going to be very accurate. So this is the better drawing. And the reason for this is molecules aren't 2D, right? They don't lay flat on a page. They actually take up three-dimensional space. And so the system that's used to describe this is called VSEPR theory, or VSEPR theory. Whoop. It's valence shell, electron, pair, repulsion. It sounds way more complicated than it is, but really all VSEPR theory says is that electrons don't like being close to one another. Specifically, they don't want to be close to other pairs of electrons. Does that make sense? Does anybody know why? Why don't two electron pairs want to be close to one another? Because they're both negative, right? Two like charges don't want to be close to one another. Opposite charges do, but like charges repel. So this handout is really helpful, this VSEPR and the shapes of molecules. And the central takeaway I wanted to show you is on the left-hand side. So in this column right here, what this is basically telling you is the number of lone pairs and atoms around a central atom. So number of lone pairs and bonded atoms. Right? So for example, if you look at the pink one, the number 2, you've got a central atom there. That's the one in gray, kind of right here. And then it's got 2 atoms on either side and no lone pairs. This is referred to as a linear molecule. And it makes sense that this angle here between that atom and that atom is going to be about 180. That way the electrons in those bonding pairs are on opposite sides. Does that make sense? They don't want to be 90 degrees because they can be further away than that. So we've got a linear molecule anytime you have a central atom with 2 bonded atoms. All right, then the next class, that's the green class below it. It's kind of teal, I guess. If you have a central atom and then 3 bonded atoms around it, now those atoms prefer to be 120 degrees apart, right? So kind of form a triangle. That way they're evenly spaced. You can also have another one that looks pretty similar, where instead of an atom in this top position there, you could have a lone pair occupying that space. It adopts a similar geometry because that lone pair wants to occupy its own private space away from the other atoms. All right, and then down on the bottom, we've got a situation where you have a central atom with 4 bonded atoms. That's this one right here. And when you do that, it actually doesn't form a cross. It actually forms more of a pyramid, right? So 3 legs of a stool and then one sticking out the top. That gets those atoms as far away from one another as possible. Additionally, you can swap out one of those atoms for a lone pair, like with that one, and then you end up with what looks like stool legs and then a lone pair sticking up. That also has similar geometry. Or, as in the case with water, you can have 2 lone pairs and then 2 legs kind of sticking up in the air. These each have their own unique names, and these are names I do want you to know. So, for example, this one's tetrahedral. It's already on your chart. I'm just drawing it so you can see it better. That one's tetrahedral. You can think of a tetrahedron like a pyramid. And then this one is trigonal pyramidal. That one is a little bit more pyramid-like than the other one. It's not a true tetrahedron because it only has those legs. And then this one over here is referred to as bent. Just to make things confusing, because it's chemistry, you notice how this one and this one look really similar? They both kind of have atoms that are bent in relationship to one another. They're both called bent. The last one, or last 2, are pretty easy. This one right here, where you've got evenly spaced atoms in 120 degrees, that's called trigonal planar. And then the last one up above, it's nice and easy, and this one is linear. Does that make sense?
How's the question on a test go?
It'll be very similar to the worksheet, so I'll walk you through a few examples and get you used to it, because I know it takes a while to get used to these. The main thing, too, is to know the overall shape of these molecules, whether or not it's linear, trigonal planar, bent, tetrahedral, or trigonal pyramidal. In addition, some instructors will even ask you about what they call electronic geometry. And electronic geometry is referring to which class it falls into. Does it fall into the first, second, or third class? And so, for example, the class 2 here would be a linear electronic geometry. The next one is a trigonal planar. Electronic geometry. And then the last one is your tetrahedral. The way I kind of describe this to people is it's kind of like in biology when you're describing a species. You can say, oh, it's a mammal. But more specifically, you can say what type of mammal it is. The one in blue on the far left-hand side is the more generic term describing the overall electronic geometry. The names in red are the more specific ones. So in general, when I'm asking you about shape, I'm asking you about the more specific shape. If you look at the bottom down here, there's two more classes, the 5 and 6. If you go on to Gen Chem, you will cover it then. We're going to skip it for this class just because we're not going to run into too many examples. There's a lot of weird shapes you can get in chemistry. Does that make sense? So we're going to practice that with model kits. It takes a little while to get used to. The main thing I want you to do is remember these shapes for that first exam and know how to draw Lewis structures. That's one of the more challenging parts. But once you get it, it tends to stick. So if you are struggling, please go to the WTC or schedule an appointment. All right, one last thing before we get going with our model kits. It's describing polar versus nonpolar molecules. Oops. So going backwards, can't draw an E today. Bonds are polar if there is an imbalance in electron density. Between two atoms. Right, so we just did that with those arrows. Molecules as a whole can actually have polarity too, so we need to talk about that. So molecules can have a net polarity. This is called a dipole. If there is an overall imbalance of electron density. And I'll show you what I mean by this because it does seem a little bit weird making this distinction between a bond and a molecule being polar. So let's take a look at an example here. Let's do boron trifluoride, that's BF3. And we'll draw the Lewis structure over here. And then we'll do its 3D shape over here. And then we'll determine if there's a net dipole. Not individual dipoles, but this time a net dipole. So for example, with boron, I put it in the center. I'd say 3 fluorines around it, like that. How many valence electrons for boron? What row or column is it in? 3A. So I go 1, 2, 3. Fluorine should have 7. Again, you can pair these up, so it looks like we can easily pair those up, and those up. So I'm going to go ahead and just redraw it. So this would be the Lewis structure for boron trifluoride. However, do you think that's a good representation of the three-dimensional shape for boron trifluoride? Yeah, right here, it looks like I've got it as 90 degrees. It's probably not going to be 90 degrees. What would be a better angle?
120.
120, absolutely. So if we think about the three-dimensional shape, it'd be better to have those fluorines evenly spaced around the boron, right? That way we can maximize the distance between electrons and keep this at 120 degrees. What's the geometry of this? What's the overall shape described as? Trigonal planar. All right, so that's the overall 3D shape. Now the tricky thing is determining whether or not there's a net dipole. But in order to determine that, we first start out to doing individual dipoles. So what do you think's more polar, boron or fluorine? Fluorine. Fluorine's the most electronegative atom. So what I would do is with my individual dipoles, I'd say, all right, that boron's going to suck the fluorine's going to suck electron density away from that boron on all of these sides, right? All right, so there are individual dipoles. So I'm just going to label that. Actually, I'll keep the color different. Meaning there's an imbalance of electron density between the boron and fluorine. But if you think about the overall molecule, do you think the overall molecule has a net imbalance of electrons? Yeah, it's kind of weird, but the fluorines are evenly spaced around it, so they're pulling equally in opposite directions, right? So in this case, they actually cancel out their individual dipoles, and there's no net dipole. And that's because the individual dipoles cancel in 3D space. Does that make sense? All right, we'll do one more and then we'll jump into the model kits. So same sort of thing, we'll do Lewis on the far left-hand side. We'll do 3D. And then we'll do net dipole over here. All right, so this compound will do nitrogen trifluoride, so NF3. So same thing with Lewis. Do nitrogen in the middle, do 3 fluorines. How many valence electrons for nitrogen? 5. And then we've got 7 for fluorine. There we go, and now we can pair up these nitrogens with the fluorine, which means our Lewis structure for nitrogen trifluoride still have a lone pair on the nitrogen. And it would look like this. Is everybody on the same page so far with that? All right, now the tricky thing, the three-dimensional shape. What would the shape be described as if you have 3 bonded atoms and 1 lone pair around a central atom?
The trigonal
Trigonal pyramidal, right? All right, so if we try to draw this, it gets trickier as you have three-dimensional space. But what you can do is say, all right, it's kind of like table legs. When I draw it as a wedge, that means it's kind of sticking out towards you. And then as a dash, that means it's going away from you. So this is kind of like a stool with 3 legs. I'm going to make a note that dash equals back, wedge equals forward. Chemists do this to give a little bit of perspective. And then if you think about the lone pair is basically in this orbital, just hanging out above the nitrogen like that. So this would be described as trigonal pyramidal. All right, now what we do, just like before, is find individual dipoles. So if between nitrogen and fluorine, which one's more electronegative? Fluorine. Fluorine's the king of electronegativity. So we can draw dipole arrows kind of like that. Each of these fluorines is hogging electron density from that nitrogen. And if you look at this, does it look like the net dipoles are canceling out? No, they're all pointed in the same direction. They're all kind of in net pointed down towards the bottom of the page. So in this case, there would be a net dipole. Since the dipoles don't cancel. And what some chemists really like to do is to draw a net dipole arrow. So for example, if you average all 3 of those red arrows, you can say the net imbalance of electron density is kind of pointed towards the bottom like that. So this would be a net dipole arrow. Does that make sense?
Like if you split it in half, there's not an equal balance on each side.
Yeah, exactly. You kind of have to look at the tug of war and which side of the molecule is winning the tug of war. If one side is winning, the net dipole arrow is going to be pointed towards that side of the overall molecule. So net dipole is different than individual dipoles. Yep.
Does it have to go through the molecule? Can I put it below like the middle fluorine instead of, or do I need to draw it completely through to?
Most people will show it completely through because if you look at that lone pair side, right, above the nitrogen, that's actually electron poor. It doesn't have as much electron density as it would like. And then the underneath side is the side that's really electron rich. So we draw the arrow going through the entire molecule.
Okay.
Does that make sense?
Yes.
All right. So what I want to do is try to get you started on today's activity. So if you've got the activity, let's pull that out. And I forgot on here, please put your name. I can't grade you if you don't have your name on there. I guess I could just give everybody 100%, but.
Yes. I like that idea.
So let's do the first 2 as a group. The first one and second one are actually your problem of the day problems. So if you got those wrong, I'll actually give you a do-over on your pod. You can grab it and correct it. So let's do the first one. It's a compound of all carbon and fluorine. So if we draw the Lewis structure for this, we got carbon, we've got 4 chlorines. Chlorine has 7 valence electrons, right? And how many valence for carbon? 4, so 1 on each side. So if we go ahead and look at this, we compare this one up. Whoops, forgot my electron there. That one up, and that one up. I just like to keep things clean and simple, so instead of drawing those as circled pairs of electrons, I'm just going to show that as bond lines, because we know that there's a shared set of electrons between there. All right, and then in the next part, it says, what's the number of atoms plus lone pairs, and assume that this is referring to the central atom. All right, so if we look at the central atom for this structure, it's carbon, right? If we count the number of bonded atoms to carbon, there's 4. There's 0 lone pairs, so we'd say the net would be 4 there. All right, if we think about the electronic geometry, what should it be? What do you think? Be tetrahedral, absolutely. All right, and then same thing, number of atoms bonded around carbon we said was 4. Number of lone pairs we said is 0. What's the more specific geometry? And it can be the same. Just tetrahedral. So sometimes your molecular geometry and electronic geometry are described the same way.
A lone pair would just be like a hydrogen sticking up, right?
A lone pair would just be a pair of electrons, no bonded atom. So we'll actually see that in our next example. Yeah. Okay, so let's try to do a 3D sketch. A tetrahedron has one part sticking up like that. One chlorine would be out like that. One would be kind of like a leg sticking towards you as a wedge. So you remember wedges mean they're coming out towards you. And another one would be sticking out like that. What I want you to do is to actually try to build these using the model kit. That way you can see 3-dimensionally what the shape looks like and then try to do the 3D sketch that matches this. All right, if we look at this really quickly, I know that chlorine's in the top right-hand corner of the periodic table. So that means chlorine's going to pull electron density away from the chlorines. Do you think there's a net dipole, meaning is the molecule polar or nonpolar? Why would it be nonpolar?
All 4 directions.
Yeah, it's pulling in equal and opposite directions. So in this example, it'd be nonpolar because each of those individual dipoles are pulling in equal and opposite directions. Does that make sense? We'll do one more. This was kind of an easier one to get started with. Next one we'll do is the CH3OH. Again, this was one I wanted you to try on your problem of the day. So I'm just going to evenly space these around. Carbon we know has 4 electrons. Hydrogen has 1. Oxygen has 6. And hydrogen has 1. So just like before, I could say, let's pair these up, these up, these up, these up. We already have a pair up there, so that's good. Pair here, that's good. And then we pair up this remaining set. So I'm going to go ahead and change this to bond line notation, just to try to keep it neat and tidy. So we've got a bonding pair there, 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 and there. And then up here and here, we've got lone pairs. Does that make sense? All right, for the first one, it just says what's the number of atoms and lone pairs. It's not clear which atom it's referring to, so we'll do both. So just over here, all right, carbon. And then down here, I'll write oxygen. Whoops. Because both of them are kind of central atoms with other things bonded to them, right? Okay, so if we look at carbon, how many bonded atoms plus lone pairs do we have? 4, right? We have 4 bonded atoms and no lone pairs for carbon. All right, how many for oxygen?
4.
We've got 2 bonded atoms and 2 lone pairs. So combine both of those, we'd have 4. All right, what's the electronic geometry for carbon?
I'd be going to it.
Using that handout, cheat sheet. Tetrahedral. All right, electronic geometry for oxygen, that's the more generic term on the far left-hand side of our notes. What would that be for oxygen if it has 4 things around it? So more specifically be bent, but the electronic geometry is the really general one. So this would also be tetrahedral. However, like we said, the specific geometry for oxygen would be bent. So this is the specific. The electronic one is the generic layout. All right, what's the molecular geometry of carbon? If it has 4 things around it, no lone pairs, tetrahedral. So like I said, sometimes the specific layout and the specific shape, or sorry, the generic layout and the specific shape are the same.
When you're counting the right atoms, do you count essential as well?
So for example, what I'd be doing for carbon is just focus on carbon and say, what's around carbon?
Right.
We've got 4 attached atoms. That means that the shape of carbon is tetrahedral versus the shape for oxygen, which would be bent.
You're counting oxygen, hydrogen, hydrogen, hydrogen.
So for example, let's say I'm focusing in on oxygen here.
Right.
I'd say, what's the molecular geometry for that oxygen atom? We know it has 2 bonded atoms, 1 hydrogen and 1 carbon, and then it has 2 lone pairs.
Right.
So anytime you have 2 atoms bonded and 2 lone pairs attached, that means your overall shape is going to be bent.
Okay.
Does that make sense? All right. Then the tricky thing, again, is determining the 3D sketch. So just like before, we'd say we've got a central carbon atom. Actually, let me keep it the same color. That's tetrahedral. So it's got this tetrahedral layout with the dash and a wedge, but one of those legs must now be an oxygen. And then this oxygen, we know the hydrogen doesn't come off like that. It's not linear. We actually need to show it with a bent shape, which you should be able to see with the model kit. And then both lone pairs are kind of hanging out like that. So now again, we want to show net dipoles. We said carbon and hydrogen bonds really don't have a net dipole, right? There's not a big difference. What's more electronegative between oxygen and carbon, though? Oxygen. So I'd say, all right, it's hogging electron density. How about between the oxygen and the hydrogen? Oxygen. It's the same thing. It's going to pull electron density. If we think about the net dipole, we average those 2 together. It's actually going to be pointed down towards that lone pair side. Does that make sense? In this case, they're not canceling out because they're not pulling equally in opposite directions. So is this polar or non-polar?
Non-polar. Polar, sorry.
Polar, exactly. Does that make sense? What I want you to do is to try working on this all week. If you have questions about it, please let me know. My goal isn't to leave you behind in the dust. We can go over this again in lecture. But what I want you to do today is to come up and grab a kit. When you open the lid, you'll see on the back it has a list of what each kit should contain. That means we don't want to mix up the kits. In addition to that, in general with these kits, the red balls are for oxygen, the black balls are for carbon, the blue balls are for nitrogen and phosphorus, so you want to choose the correct color. If you need to make a double bond, you may need to use these flexible ones because you'll have to add 2 of them. So if you ever need help with the double bond, raise your hand and I can try to help you show how to make a double bond. Does that make sense? All right, so we'll get going with this. Like I said, my goal is for everybody to get 100% on this. I don't want to leave anybody behind.